March 7, 1944. 32,000 feet above the Ruhr Valley, Flight Lieutenant David Walsh felt his Spitfire's Merlin engine shudder violently as he pushed the throttle past emergency power. The supercharger boost gauge climbed through 60 inches, 62, 65. Then the detonation began. Sharp metallic knocks that sounded like someone hammering rivets inside the cylinder heads. Every RAF pilot knew that sound meant one thing: pull back the throttle immediately, or watch your engine destroy itself in the next 30 seconds. Walsh had no choice. Below him, a formation of Messerschmitt 109s was climbing to intercept a damaged Lancaster struggling home from a raid on Essen. The bomber crew needed another 2 minutes to reach the safety of Allied fighter cover. 2 minutes that Walsh's Merlin engine couldn't give him at combat power without tearing itself apart from the inside. He backed off the throttle to 55 inches of boost, the maximum. Sustainable power that Rolls-Royce engineering manuals insisted represented the absolute limit of what the Merlin's ignition system could handle. The German fighters continued their climb, pulling away from his Spitfire as physics and engineering conspired to make altitude belong to whoever could generate more power without exploding their engine. The Lancaster went down 7 miles short of Allied lines, all 7 crew members lost. Walsh's after-action report included the bitter notation that another 5 inches of manifold pressure, just 5 more inches, would have given him the climb rate to stay with the German fighters and protect the bomber. But those 5 inches represented more than a mechanical limitation. They embodied the fundamental problem that had plagued high-altitude combat since the war began: how to extract more power from an aircraft engine without the ignition system triggering catastrophic detonation. At Rolls-Royce's Derby facility, Chief Development Engineer Stanley Hooker read Walsh's report with mounting frustration that mirrored the feelings of every engineer working on the Merlin program. The engine's design was fundamentally sound. Sophisticated supercharging systems compressed intake air to generate power at altitudes where atmospheric pressure alone would starve the engine. Precision-machined components tolerated enormous stresses. Advanced metallurgy prevented catastrophic failures under extreme conditions. But the ignition timing system, the mechanism that determined precisely when spark plugs fired in relation to piston position, remained stuck in engineering principles developed before anyone imagined aircraft engines operating at boost pressures exceeding 60 inches of mercury. The mathematics of internal combustion established the core challenge with unforgiving clarity. As manifold pressure increased, air and fuel mixture density rose proportionally. Higher density meant the mixture burned faster after ignition, releasing energy more rapidly and generating higher peak pressures inside the cylinders. Beyond a certain threshold, that pressure rise became so violent that it qualified as detonation rather than controlled combustion. Detonation created shock waves that hammered piston crowns, cylinder heads, and connecting rods with forces capable of destroying engine components in minutes. The only proven solution was limiting boost pressure to levels where detonation couldn't occur, but that solution meant accepting German fighters could outclimb British aircraft at critical altitudes. Hooker had assembled his senior engineering staff for an emergency conference on March 15th to address what operational squadrons were calling the altitude crisis. German fighters, equipped with nitrous oxide injection systems, were achieving combat power at altitudes where Merlin engines struggled to maintain normal operation. The tactical implications threatened to undermine British air superiority over Western Europe at precisely the moment when invasion planning demanded absolute control of European skies. The Merlin 66 engine generates 1,800 horsepower at 55 inches of boost at 30,000 feet, Hooker began, his tone carrying frustration born from months of incremental improvements that never quite solved the fundamental problem. Our calculations show we could achieve 2,100 horsepower at 72 inches if we could prevent detonation at those power levels. That additional 200 horsepower would give Spitfires the climb rate to dominate German fighters at any altitude. But every attempt to run sustained boost above 60 inches results in destructive detonation within minutes. Senior engineer Malcolm Campbell represented the conservative faction that believed the solution lay in improved fuel formulations rather than mechanical modifications. We're already running 150-octane fuel that would have been considered impossible 5 years ago. The chemical engineers have extracted every possible anti-knock property from available fuel stocks. Pushing boost higher without better fuel is asking for detonation, no matter what mechanical changes we implement. But a younger engineer named Ronald Harker, recently promoted to ignition systems development, had spent the past month analyzing detonation patterns in test engines run beyond normal operating limits. His findings suggested that fuel quality wasn't the limiting factor that everyone assumed. "Ron," Hooker said, recognizing Harker's raised hand, "you've been running the overboost destruction tests. What are your observations?" Harker stood, consulting notes that represented dozens of destroyed test engines and hundreds of hours analyzing failure patterns. "Sir, the detonation consistently initiates during the final phase of the combustion cycle after peak cylinder pressure has already occurred." If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Standard ignition timing sets spark advance to optimize combustion for normal boost pressures. But at higher boost levels, that same timing causes the fuel-air mixture to still be burning when the piston starts its downward stroke. The late-stage combustion creates pressure waves that reflect off cylinder walls and trigger detonation. The room fell silent as engineers absorbed the implications. Conventional wisdom held that detonation resulted from excessive cylinder pressure during compression, making the fuel-air mixture unstable before ignition even occurred. Harker was suggesting that the problem lay not in the mixture's inherent instability, but in how the ignition system's timing interacted with the faster burn rates of denser fuel-air charges. "If late combustion is causing detonation," Campbell said slowly, "then advancing the spark timing earlier in the compression stroke should allow combustion to complete before the piston reaches bottom dead center. But that contradicts every principle of ignition timing optimization we've developed over the past 20 years. Harker nodded, anticipating the objection. "Conventional timing optimization assumes we're trying to achieve peak cylinder pressure at the most mechanically efficient point in the power stroke. That's correct for normal operating conditions. But at extreme boost pressures, mechanical efficiency becomes secondary to preventing detonation. If we advance spark timing significantly earlier than optimal, we accept some efficiency loss in exchange for completing combustion before detonation conditions develop." The concept seemed to violate fundamental thermodynamic principles. Igniting the fuel-air mixture too early meant fighting against rising compression pressure, wasting energy that should be converted to useful work. Advanced timing also meant higher peak combustion temperatures, potentially causing other forms of engine damage. Every engineering calculation suggested that aggressive spark advance would reduce power output even if it prevented detonation, making the modification pointless for improving combat performance. But Harker had one more piece of evidence, data from an unusual source that suggested conventional calculations might be missing something crucial. A maintenance crew at RAF Biggin Hill had reported an anomaly 3 weeks earlier. One of their Spitfires had returned from combat with a damaged magneto, the mechanical device that generated high-voltage current for spark plugs. The magneto's internal timing had been knocked out of adjustment, advancing spark timing by approximately 15 degrees beyond normal specifications. Ground crews assumed the mistimed ignition would cause the engine to run rough or fail completely. Instead, test pilot squadron leader James Morton reported that the aircraft climbed better at high altitude than any Spitfire he had previously flown. The engine ran smoothly at boost pressures that would normally trigger detonation, and power output seemed higher rather than lower, despite the grossly incorrect ignition timing. Morton's report had been filed as an interesting anomaly, probably explained by variations in fuel quality or atmospheric conditions. But Harker recognized it as potential evidence that advanced ignition timing, far from reducing power at high boost, might actually enable the engine to run at pressures that would otherwise cause immediate detonation. Hooker leaned forward, his engineer's instinct recognizing the significance of what Harker was proposing. "You're suggesting we deliberately mistune the ignition system, advancing spark timing beyond anything that thermodynamic optimization would recommend, purely to prevent detonation at extreme boost pressures. Precisely, sir. The power loss from inefficient combustion timing will be more than offset by our ability to run sustained boost at 70 inches instead of 55. The additional manifold pressure provides so much more fuel and air that the engine's power output increases dramatically, even with suboptimal ignition timing. The proposal represented the kind of counterintuitive thinking that either produced breakthrough innovations or catastrophic failures. Campbell immediately voiced the concerns that every conservative engineer in the room was thinking. Ron, deliberately advancing ignition timing will create enormous mechanical stresses on connecting rods and crankshaft bearings. The pressure rise during compression will be working against piston motion, potentially causing structural failures we've never seen before. We could solve the detonation problem only to have engines tear themselves apart from excessive compression loading. Harker had anticipated this objection during his weeks of analysis. The mechanical loads will increase, but our stress calculations show they remain within design margins for the Merlin's forged crankshaft and heavy-duty connecting rods. The engine was deliberately overbuilt to handle combat abuse. We have structural strength margin that we've never fully utilized because detonation limits always stopped us from reaching maximum boost before mechanical limits became relevant. The engineering debate continued for another hour, with senior staff divided between those who recognized the revolutionary potential of Harker's proposal and those who believed it represented dangerous improvisation that contradicted fundamental principles of engine design. The discussion might have remained theoretical indefinitely, except for a telegram that arrived from Air Ministry headquarters at 4:15 that afternoon. The message reported that German fighters had shot down 11 RAF aircraft over Berlin the previous day, with most losses attributed to the Luftwaffe's altitude advantage during initial engagement. Operational squadrons were requesting emergency authority to run Merlin engines beyond rated boost limits, accepting shortened engine life in exchange for the power needed to compete with German fighters at extreme altitudes. Hooker recognized that the decision could no longer be delayed. "Gentlemen," he announced, his tone carrying the weight of institutional authority, "we will conduct immediate testing of advanced ignition timing at extreme boost pressures. Ron, you have authorization to modify 3 test engines with variable timing systems that can be adjusted during operation. We'll run controlled destruction tests to determine if your theory about late-stage detonation is correct and whether advanced timing actually prevents it." As the meeting dispersed, Harker felt the enormous weight of professional responsibility settling on his shoulders. The next few weeks would determine whether his analysis of detonation mechanisms was brilliant insight or fatal miscalculation. Either way, the lives of RAF pilots flying combat over Europe now depended on whether an electrician's understanding of ignition timing could unlock power levels that every engineering textbook said were impossible to achieve safely. The test cells at Rolls-Royce Derby had witnessed countless engine failures over the years, but the methodical destruction of Merlin engines that began on March 20, 1944, represented something different from normal development testing. Harker's team wasn't trying to improve reliability or optimize efficiency. They were deliberately pushing engines beyond every known operational limit to understand precisely how and why they failed. The first test engine, a Merlin 66 modified with adjustable ignition timing, was bolted to a test stand that measured power output, manifold pressure, cylinder head temperature, and a dozen other parameters in real time. Harker stood in the control room, his hand on the boost control lever, while senior observers watched through thick safety glass designed to protect them from catastrophic engine explosions. "Standard ignition timing, 55 inches of manifold pressure," Harker announced, setting baseline parameters that represented normal maximum combat power. The Merlin roared at full throttle, its supercharger compressing intake air to densities that produced 1,800 horsepower. All parameters showed normal operation, exactly as expected. "Advancing boost to 60 inches, Harker continued, pushing the engine into the region where detonation typically began. The cylinder pressure traces on the oscilloscope showed normal combustion patterns for several seconds. then the characteristic sharp spikes that indicated detonation had initiated. The test engine was shut down immediately, having demonstrated precisely the behavior that limited Merlin engines to 55 inches of sustained boost in operational service. The second test run began with ignition timing advanced 15 degrees beyond normal specifications, matching the accidental mistiming that the Biggin Hill maintenance crew had discovered. Harker brought the engine to full power with standard boost, noting that cylinder head temperatures ran slightly higher than normal, but remained within acceptable limits. "Advancing boost to 60 inches, he announced, his voice tight with anticipation. The Merlin's note deepened as the supercharger forced more air into the intake manifold. Cylinder pressure traces showed combustion completing earlier in the power stroke than normal, exactly as Harker's theory predicted. Most importantly, no detonation spikes appeared on the oscilloscope. The engine ran smoothly at 60 inches of boost with advanced timing, producing power that would have been impossible with standard ignition settings. 65 inches, Harker said, pushing into territory that had destroyed dozens of test engines during previous development programs. The combustion traces remained clean. Cylinder head temperatures climbed but stayed within acceptable ranges. Power output reached 1900 horsepower, 100 horsepower more than rated maximum, with none of the detonation that should have destroyed the engine within seconds. 70 inches, Harker announced, his voice barely audible over the Merlin's thunderous roar. The boost pressure that Stanley Hooker had identified as necessary for altitude superiority over German fighters. The test cell vibrated from the engine's fury. Every gauge showed parameters at or beyond normal maximum limits. But the oscilloscope traces remained clean, showing fast, complete combustion with no hint of the detonation that everyone had believed was inevitable at such extreme boost pressures. 2100 horsepower, Chief Test Engineer William Taylor called out, reading the dynamometer output. That's 300 horsepower above rated maximum, and the engine is still running clean. The test continued for 5 minutes at 70 inches of boost before Harker reduced power, shut down the engine. Maintenance crew swarmed the test stand, removing cylinder heads and inspecting internal components for damage that everyone assumed must have occurred despite the clean operating data. What they found defied expectations shaped by decades of engine development experience. The piston crowns showed normal combustion deposits with no evidence of detonation damage. Cylinder heads were unmarked by the characteristic erosion that excessive heat and pressure would have caused. Connecting rods and crankshaft bearings showed wear patterns consistent with normal high-power operation. The Merlin had run at boost pressures that should have destroyed it within minutes, and emerged with nothing more than routine wear. Malcolm Campbell examined the stripped engine with the expression of a man watching his professional certainties crumble. This contradicts everything we know about ignition, timing, optimization. The advanced timing should be causing enormous mechanical stress from fighting compression pressure, yet the engine shows no structural damage at all. Harker had spent the previous weeks preparing for this moment, and his explanation revealed why conventional engineering wisdom had failed to predict the advanced timing's success. The key is understanding that we're not optimizing for peak thermodynamic efficiency anymore. At 70 inches of boost, the fuel-air charge is so dense that it burns completely in half the time required at normal boost pressures. Standard ignition timing was designed for slower burn rates at lower manifold pressures. When we try to use that same timing at extreme boost, combustion extends too far into the power stroke and creates the pressure oscillations that trigger detonation. By advancing timing significantly, we're compensating for the faster burn rate. Combustion still completes at roughly the same point in the power stroke relative to piston position, just earlier in absolute terms. The engine doesn't know or care that we're using incorrect timing by conventional standards. It only responds to whether combustion pressure peaks at the right moment to prevent detonation. Stanley Hooker had arrived in the test cell during the engine's disassembly, and his presence signaled that Harker's experimental success had attracted attention at the highest levels of Rolls-Royce's engineering. Hierarchy. "Mr. Harker," Hooker said formally, though his tone carried unmistakable satisfaction. "You appear to have solved a problem that has limited Merlin performance for 2 years. The question now is whether your solution can be implemented quickly enough to affect combat operations. The transition from successful test to operational deployment presented challenges that went far beyond simply advancing ignition timing on production engines. The Merlin used two magnetos, mechanical devices driven by the engine that generated precisely timed high-voltage pulses for spark plugs. Adjusting magneto timing required careful calibration to ensure all 12 cylinders fired at the correct moment relative to piston position. More critically, the advanced timing had to be adjustable in flight. Pilots needed the ability to use standard timing for takeoff and cruise, where the advanced settings would cause rough running and reduced efficiency, while switching to advanced timing for combat power at high altitude. Harker's team had already begun designing a dual timing system that would allow pilots to select between normal and combat ignition settings, but implementing the modification across operational Merlin engines would require coordination between Rolls-Royce, Air Ministry maintenance authorities, and squadron-level mechanics. The first production trial installation occurred on April 2 at RAF Duxford, where squadron leader Alan Deer's Spitfire received the modified ignition system that everyone was already calling Harker's wild timing. Deer, a New Zealand ace with 22 confirmed victories, approached the modification with the healthy skepticism of a combat pilot who had learned not to trust engineering promises until proven in actual flight. Ground testing showed the modified engine ran smoothly at cruise power with normal timing, then transitioned cleanly to advanced timing when Deer activated the combat ignition switch. But the real test would come at altitude, where detonation had always limited Merlin performance regardless of what worked perfectly on the ground. Deer took off from Duxford at dawn on April 4th, climbing to 35,000 feet over the North Sea. The standard timing carried him through the ascent with familiar smoothness, the Merlin running exactly as designed for normal operations. At altitude, cruising at 50 inches of boost, he activated the combat ignition switch that Harker's team had installed on his instrument panel. The transition was immediate and dramatic. The engine note changed subtly, acquiring a harder edge that suggested barely restrained violence. Deer advanced the throttle cautiously, watching the boost gauge climb through 60 inches, then 65. The Merlin responded with smooth, progressive power that showed none of the threatening vibration that normally preceded detonation. At 70 inches of manifold pressure, the Spitfire accelerated with authority that Deer had never experienced at such extreme altitude. "Duxford Control, this is Blue Leader," Deer radioed, his voice carrying the excitement of a pilot discovering his aircraft had suddenly gained capabilities that redefined what was possible. "I'm indicating 70 inches of boost at 35,000 feet with no detonation. Climb rate is 2,200 feet per minute." This is absolutely remarkable performance. The climb rate represented a 50% improvement over what the same Spitfire could achieve with standard timing at identical altitude and boost pressure. More importantly, the engine showed no signs of the destructive detonation that had always limited high-altitude combat power. Deer spent the next 20 minutes exploring the modified engine's capabilities, pushing boost pressures and altitude limits that would have been suicidal with conventional ignition timing. At 40,000 feet, an altitude where Merlin engines typically struggled to maintain level flight, Deer's modified Spitfire still generated enough power for combat maneuvering. The tactical implications were immediately obvious to any combat pilot. German fighters that had dominated high-altitude engagements through superior power now faced British aircraft that could match or exceed their performance at any altitude. The test flight data convinced Air Ministry officials to authorize emergency modification of operational Spitfires beginning immediately. Maintenance crews at forward bases received technical bulletins describing the ignition timing changes, along with authorization to implement modifications using existing magneto adjustment procedures. The simplicity of the modification proved to be one of its greatest advantages. Unlike complex mechanical changes that required specialized tools and extensive training, adjusting magneto timing was a standard maintenance procedure that any competent aircraft electrician could perform in under 2 hours. By April 15th, over 60 Spitfires equipped with Harker's wild timing were operating from bases across southern England. Pilots reported universally positive experiences, describing power and climb performance that transformed high-altitude combat from a desperate struggle against German advantages into domination through superior engine output. The first major combat test of the modified engines came on April 22 during a massive raid on Stuttgart. Wing Commander Douglas Bader led 48 Spitfires as high cover for the bomber stream, climbing to 38,000 feet to intercept German fighters, attempting to attack from above. The Luftwaffe had developed this tactic specifically to exploit British fighters' inability to maintain combat power at extreme altitude. Bader's modified Spitfires arrived at interception altitude with enough power reserve to engage German fighters in turning combat rather than simply maintaining defensive formations. Hauptmann Heinrich Oehler led the German interception force, 24 Messerschmitt 109s from Jagdgeschwader 7-7. Oehler had flown over 300 combat missions, and his tactical experience had taught him that British fighters became progressively weaker as altitude increased. Above 35,000 feet, Spitfires could barely maintain level flight at combat power, making them easy targets for German fighters operating at their optimal performance envelope. The engagement that developed over Stuttgart shattered Oehler's expectations, shaped by 2 years of high-altitude combat experience. Bader's Spitfires didn't struggle to maintain altitude. They climbed aggressively to meet the German fighters, their Merlin engines generating power that seemed impossible at such thin air density. The turning combat that followed demonstrated how completely Harker's ignition timing modification had altered the tactical balance. British pilots found their aircraft responsive and powerful at altitudes where previous combat had required constant attention to maintaining basic flight control. They could maneuver aggressively, pursue climbing opponents, and maintain sustained combat power without the detonation that had always forced them to reduce boost at critical moments. Oehler's after-action report to Luftwaffe headquarters described British fighters displaying unprecedented high-altitude performance. The Spitfires climbed and fought at 38,000 feet with power output that exceeded anything we have encountered previously. Our altitude advantage has been completely negated. The enemy aircraft maintained full combat capability at heights where they should have been nearly helpless. German intelligence officers received Oehler's report with considerable skepticism. Luftwaffe technical staff knew the limitations of British Merlin engines at high altitude. Those limitations were fundamental to German tactical doctrine for high-altitude combat. The possibility that British engineers had somehow eliminated those restrictions seemed implausible. Yet combat reports from multiple units told consistent stories of Spitfires operating effectively at altitudes that should have been beyond their capability. Major Wilhelm Specht, responsible for evaluating enemy aircraft performance, requested immediate analysis of any captured British fighters to determine if mechanical modifications explained the reported performance improvements. His directive reached Luftwaffe maintenance units throughout occupied Europe, with orders to pay particular attention to engine modifications on any Spitfires forced down in German-controlled territory. The captured evidence arrived on May 3, when Flight Lieutenant Robert Stanford Tuck was forced to crash-land his damaged Spitfire near Abbeville after an engagement with Focke-Wulf 190 fighters. German recovery teams secured the aircraft before Stanford Tuck could fully destroy the engine, and the relatively intact Merlin was transported to the Luftwaffe testing facility at Rechlin for detailed examination. Oberst Heinz Breer, chief engineer at Rechlin, personally supervised the inspection of Stanford Tuck's captured Merlin engine. The external examination revealed nothing unusual. Standard Rolls-Royce construction, normal supercharger configuration, typical fuel injection system. But when mechanics removed the magneto covers to check ignition system condition, they discovered timing settings that made no sense according to conventional engine design principles. The magnetos were adjusted to fire spark plugs, approximately 15 degrees earlier in the compression stroke than normal Merlin specifications indicated. Breer's initial assumption was that British maintenance crews had simply mistimed the ignition system, perhaps due to wartime shortcuts in training or quality control. But the precision of the timing adjustment, identical on both magnetos and clearly marked with fresh calibration paint, suggested deliberate modification rather than maintenance error. The Rechlin test facility mounted the captured Merlin on a test stand for operational analysis. Running the engine with its advanced timing at normal boost pressures produced slightly rough operation and reduced efficiency, exactly what conventional engineering predicted. But when test engineers increased boost toward combat power levels, the advanced timing's purpose became clear. The engine ran smoothly at manifold pressures that would cause immediate detonation with standard timing. At 70 inches of boost, the captured Merlin generated power output that exceeded anything Luftwaffe intelligence believed British engines could achieve. Breer's report to German aviation authorities described the advanced timing modification as an elegantly simple solution that exploited a fundamental characteristic of combustion physics that German engineers had overlooked. The British had sacrificed some efficiency at normal power settings to enable sustained operation at extreme boost pressures. The modification required no special materials, no complex manufacturing, nothing that couldn't be implemented immediately using existing maintenance procedures. The report's final paragraph carried implications that went far beyond technical admiration. If British fighters can now operate effectively at altitudes where we previously enjoyed decisive advantages, our entire defensive strategy for high-altitude bomber interception must be reconsidered. The tactical situation has fundamentally changed. German attempts to develop equivalent modifications for their own fighters revealed why the British solution had been so difficult to predict. Luftwaffe engines used different ignition systems that couldn't be adjusted as easily as British magnetos. More critically, German engine designs had evolved with different compromises between power output and reliability. The modifications that worked brilliantly for Merlin engines produced inconsistent results when applied to Daimler-Benz and BMW power plants. By late May, Harker's wild timing had been implemented on over 400 operational Spitfires, with modification programs extending to other Merlin-powered aircraft including the Hawker Hurricane and de Havilland Mosquito. The strategic impact extended far beyond individual aircraft performance improvements. The sudden British capability to contest high-altitude airspace that German fighters had previously dominated forced Luftwaffe tactical planners to abandon the altitude advantage doctrine that had guided their defensive operations since 1941. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The broader implications of the ignition timing breakthrough reached into areas of aviation engineering that went far beyond immediate combat applications. Harker's demonstration that conventional optimization principles could be deliberately violated to achieve performance goals that seemed impossible. Through traditional approaches challenged fundamental assumptions about engine design. Senior engineers at Rolls-Royce began reconsidering other aspects of Merlin development where conventional wisdom might be limiting performance. The supercharger drive ratio that everyone assumed was optimized for best efficiency became subject to experimental increases that sacrificed some mechanical reliability for higher boost capability. Fuel injection timing, that had been carefully calibrated for smooth operation, was adjusted to prioritize maximum power output even if it caused rough running at certain engine speeds. Cooling system designs that emphasized longevity were modified to accept higher thermal loads in exchange for reduced drag and weight. Each modification built on the lesson that Harker's wild timing had taught. Combat effectiveness mattered more than theoretical optimization, and engineering solutions that seemed crude or improper by textbook standards could prove superior to elegant designs when measured by operational results. The philosophical shift influenced not just Merlin development but British aviation engineering more broadly, encouraging a pragmatic willingness to challenge established principles when battlefield necessity demanded unconventional thinking. Stanley Hooker's June report to the Air Ministry quantified the impact of the ignition timing modifications in terms that made the achievement's magnitude undeniable. Spitfire combat, losses at altitudes above 35,000 feet, had decreased by 42% since the modifications began in April. British fighters were claiming German aircraft at high altitude at rates that exceeded low-altitude engagement, success, a complete reversal of previous patterns where high-altitude combat had heavily favored the Luftwaffe. Most significantly, German bomber formations were avoiding altitudes above 30,000 feet during daylight operations, effectively ceding control of high-altitude airspace to British fighters. The tactical shift demonstrated that Haake's modification had achieved not just performance improvement, but actual air superiority at altitudes that determined the outcome of strategic bombing campaigns. The personal recognition that came to Ronald Haake arrived not through official channels, but from operational pilots whose lives depended on the power his modification provided. Squadron leader James Johnson, who had flown combat missions both before and after the ignition timing changes, sent a letter to Rolls-Royce that captured the modification's human impact more effectively than any technical report. Before your timing adjustment, high-altitude combat meant carefully managing engine power to avoid detonation while trying to maintain position against German fighters that could climb away whenever they chose. Every engagement felt like fighting with one hand tied behind your back. Now we climb and fight at 40,000 feet with confidence that our engines will provide full power when needed most. The modification didn't just improve aircraft performance, it gave us back the initiative in combat, the ability to dictate engagement terms rather than simply react to German tactics. That psychological shift matters as much as the additional horsepower. The manufacturing efficiency of the ignition timing modification proved nearly as significant as its performance benefits. Unlike complex mechanical changes that required factory installation or depot-level maintenance facilities, the timing adjustment could be implemented at squadron level by trained electricians using standard tools. Aircraft could be modified overnight without removing them from operational service or disrupting combat readiness. By July, the modification program had reached Merlin engines in the Mediterranean theater, where high-altitude combat over Italy presented similar tactical challenges to those faced over Western Europe. The Pacific theater received modified engines in August, though the lower operating altitudes typical of combat against Japanese aircraft made the high boost capability less immediately critical than in European operations. The technical success of Haake's modification created unexpected challenges in other areas of aircraft operation. The significantly increased power output placed higher loads on propeller assemblies, requiring modifications to blade pitch control systems that hadn't been designed for sustained operation at 70 inches of boost. Airframe structures needed inspection for stress points that might fail under the higher acceleration loads that powerful engines could generate. Most critically, pilot training had to address the new power available at high altitude. Decades of combat experience had taught pilots to treat high-altitude flight as a regime where engine power was limited, and combat maneuvering had to be carefully managed. The suddenly available power at altitude created opportunities for aggressive tactics that pilots hadn't trained for, and several early accidents resulted from pilots overstressing airframes by maneuvering too aggressively at altitudes where aircraft had previously been power-limited rather than structure-limited. The Luftwaffe's inability to develop equivalent modifications for their own engines reflected differences in German engineering philosophy as much as technical limitations. German aircraft designers had traditionally emphasized elegant solutions that optimized multiple performance parameters simultaneously. The crude approach of deliberately mistiming ignition systems to enable operation at theoretically destructive boost pressures offended German engineering sensibilities, even as its effectiveness became undeniable through combat. The results: several German engineers, when shown captured British modifications after the war, admitted that they had considered similar approaches, but rejected them as intellectually unsatisfying. The admission revealed how strongly engineering culture could influence technical decisions, and how British willingness to accept inelegant solutions that worked had provided advantages that German pursuit of theoretical perfection couldn't match. As autumn 1944 arrived and the air war over Europe entered its final phase, the strategic implications of Haake's ignition timing modification had become fully apparent. The Luftwaffe's defensive doctrine had been built on the assumption that German fighters could dictate combat terms by maintaining altitude advantage over Allied aircraft. That assumption had shaped everything from tactical training to strategic planning for bomber interception, The sudden British ability to contest high-altitude airspace with aircraft that could generate full combat power at any altitude forced German commanders to abandon tactical approaches that had guided defensive operations for 3 years. The psychological impact of that forced doctrinal change rippled through Luftwaffe units that had built their combat confidence on altitude superiority. German pilot memoirs from late 1944 consistently mention the shock of discovering that British fighters could follow them into climbs that should have been refuge from pursuit. The summer offensive over Normandy demonstrated the ignition timing modification's operational impact at the campaign level. Allied fighters maintained continuous high-altitude coverage over invasion beaches and inland approach routes, making it impossible for Luftwaffe reconnaissance aircraft to operate above 30,000 feet without facing immediate interception. By Spitfires generating full combat power at altitudes where German intelligence had insisted British engines were barely functional. The D-Day air superiority that enabled successful amphibious operations depended partly on numerical advantage and tactical coordination, but also significantly on the technical capability that Harker's modification provided. British fighters didn't just outnumber German aircraft over Normandy. They outperformed them at critical altitudes, maintaining station and combat effectiveness in the vertical domain where German tactical doctrine had always assumed advantage. Ronald Harker received formal recognition for his contribution through the Medal of the British Empire, presented in a ceremony that Stanley Hooker attended, along with several operational pilots, whose combat success had been enabled by the ignition timing modification. The citation praised innovative engineering that materially contributed to Allied air superiority, in language that captured the achievement's significance without revealing classified technical details that remained militarily sensitive. But Harker's most meaningful recognition came from letters sent by pilots who had survived high-altitude combat that would have been fatal with standard engine timing. Flight Lieutenant David Walsh, whose report of insufficient power during a combat rescue attempt had helped catalyze the modification program, wrote that he had recently repeated a similar mission profile and successfully protected a damaged bomber through sustained high-altitude combat that his modified engine made possible. The technical legacy of the ignition timing breakthrough extended into post-war aviation development, though the modification itself became less relevant as jet engines replaced piston power plants in frontline fighters. The lesson that Harker's work taught about challenging conventional optimization principles influenced British aircraft design throughout the late 1940s and into the jet age. Engineers became more willing to question whether textbook solutions were actually optimal for specific operational requirements. The Rolls-Royce engineering culture that produced the ignition timing modification also shaped development of early British jet engines, where similar willingness to accept theoretical inefficiency in pursuit of practical performance advantages helped British designs compete with American and Soviet equivalents. The philosophical approach that Harker exemplified, prioritizing what worked over what theory said should work, became embedded in British aviation engineering practice. German post-war analysis of the ignition timing modification included grudging admiration for British willingness to implement solutions that violated engineering orthodoxy. Several former Luftwaffe engineers noted that German technical culture's emphasis on theoretical correctness had prevented consideration of modifications that didn't align with established design principles. The admission suggested that technical sophistication could become a limitation when it prevented practical solutions that simpler approaches might enable. The final measure of Harker's achievement came not from technical specifications or performance data, but from the transformed tactical reality that British pilots experienced in high-altitude combat after April 1944. Squadron commander after squadron commander reported that their pilots approached high-altitude missions with confidence rather than the resignation that had characterized such operations when engine power limitations meant fighting at severe disadvantage against German fighters. The psychological shift from defensive necessity to offensive capability reflected more than just additional horsepower. It represented the restoration of initiative, the ability to choose when and how to engage rather than simply reacting to enemy actions from position of technical inferiority. That transformation of combat psychology, as much as any specific performance metric, measured the true impact of an electrician's wild idea about ignition timing. As 1945 began and the air war over Europe entered its final months, Merlin engines running Harker's advanced timing had become standard throughout RAF Fighter Command. The modification that had started as an experimental response to a specific tactical problem had evolved into fundamental aspect of British aviation capability. New pilots entering operational squadrons learned the combat ignition system as standard procedure, unaware that it represented a radical departure from everything that engine designers had believed about ignition timing optimization. The Luftwaffe's final defensive campaigns over Germany revealed how completely the tactical situation had reversed since early 1944. German fighters that had once hunted British aircraft with confidence based on altitude advantage now found themselves hunted at any altitude, facing opponents whose engines generated full combat power anywhere German fighters could operate. The psychological impact of that reversal affected German pilot performance as significantly as any material disadvantage. Ronald Harker's post-war career at Rolls-Royce continued the pattern of challenging conventional wisdom that his ignition timing work had established. He became known as an engineer who questioned whether accepted solutions were actually optimal, and whose willingness to propose modifications that seemed theoretically wrong but worked practically pushed British engine development in directions that more conservative approaches might never have explored. The ignition timing modification remained classified until 1947, when peacetime declassification made technical details available for public discussion. Aviation journals published articles analyzing how such a simple change had produced such dramatic performance improvements, and engineering schools began teaching the story as an example of how practical requirements could override theoretical optimization in complex systems. The broader lesson that emerged from Harker's achievement transcended specific technical details about ignition timing or Merlin engines. Engineering solutions that seemed wrong according to conventional principles could prove superior to orthodox approaches when measured by operational effectiveness. The willingness to question whether established design rules actually represented optimal solutions for specific problems became recognized as essential characteristic of effective wartime engineering. As the decades passed and piston-engined fighters gave way to jets and eventually to aircraft with capabilities that would have seemed like science fiction during World War II, the story of how an electrician's wild timing adjustment transformed high-altitude combat became part of aviation history. The technical details faded in relevance as engines and aircraft evolved beyond recognition, but the fundamental lesson endured. Sometimes the most significant breakthroughs come not from sophisticated new technology or complex mechanical innovations, but from the courage to question whether what everyone knows to be true is actually correct. Ronald Harker possessed that courage, and the pilots who flew combat at 40,000 feet with engines that generated impossible power at impossible altitudes owed their lives to his willingness to challenge orthodoxy. The Merlin engines that powered British fighters through the war's final years carried within their ignition systems a testament to the power of unconventional thinking. 15 degrees of advanced spark timing, a modification so simple that any trained electrician could implement it in an afternoon, had altered the course of the air war over Europe. The simplicity itself was the genius, recognizing that the solution to a problem that seemed to require sophisticated engineering might actually lie in deliberately mistiming a system that everyone assumed was already optimized. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.